Let's start. So welcome everybody, and this is our third session on the deep dive into sensors data. My name is Jônatas. I am a developer advocate and also community manager at Timescale. And today we're going to talk about downsampling techniques that in the end, it's all about query performance techniques. And just a reminder, this is a series of sessions that we are covering as what we call template that is supposed to help folks that are in the same stage. So people are kicking off something, or they are already advanced users, so maybe they have some shared expertise that could, let's say, well, for sensors, this type of configuration works very well, and that's why we are discussing this thing. So we already built some basic settings and basic structure, and this structure is already available into our Timescale/templates in our GitHub. And this is our sensors data. So as today is the third session, we are already covered the template, and now we are covering query speed and different techniques. We are going more on downsampling algorithms today, but we can also cover any other query speed or query performance need that someone has. So if you have any problem, if you want to share it in the chat, we can try to answer it in the end of the session. And that's how we define, we say we are going to talk about sensors data, and it's very generic. We can have very different settings of sensors data, and that's why we choose for a flexible and extensible configuration. So in the template variables, we are defining the name of our objects. So the name of our hypertable, the name of our columns, how much we are going to have as all the settings, so we can concentrate it in the top of our script and then reuse it along with any template or any configuration. So that's the idea. And when we build the template, we can just refer to these previous variables. So you can say column hypertable, column segment, column payload name, and so on. And that's how we can just like incorporate the values. And binding the values, it will just be like sample, the table name, device ID, and so on. So what we get from this type of configuration is just like these automatic bindings, and then we can avoid repeating ourselves into the next configuration. So in this case, you know, this is the hypertable. In this case, we just need create hypertable function call, and it will create the metadata around this table name and inject a trigger that is like just a way that can be signaling that, hey, this table is not really a table. Now it's a kind of view that aggregates information from subpartitions, and that's how hypertable works. And when we introduced the continuous aggregates, we thought about, hey, let's just make it dynamic, so we can just make it 1 minute, 1 hour, or maybe 30 seconds for 6 hours, depending on your style. You choose different time frames, but let's make it open so people can just put the time frames, put their names, and then reuse it. And the main thing here is that the first continuous aggregates, it goes to the original table name, and the rest of the continuous aggregates, they are just rolling up in the previous time frame. So as I was explaining the hierarchical continuous aggregates, this enable us to do this roll up, and in the end, the code looks like this. So you have a time bucket, and then you have this stats egg here that is just aggregating the several types of statistics. And then you can also do a roll up in the stats egg. In the first case, from 1 hour going to 1 minute, and then you can do the same for 1 day going to 1 hour. So the idea of rolling up is just like making it very flexible, and it's also a downsampling technique. So you are also using it. But today we are going to talk about other downsampling techniques, and especially LLTB and ASAP smooth. So these are two types of let's say heuristics to solve this problem that does not need to touch your data. So continuous aggregates will materialize it somewhere, but this methodology, this is an algorithm that goes to your raw data and then extracts what you need. And in the next week, we are going to talk about another methodology that's retention. So it's also a way that you have lighter data is if you remove all the data, right? So these are different methodologies that will also make your query faster and your database lighter. And yeah, so let's start talking about a few of the advantages of using downsampling. So the first thing is memory efficiency. So when you have downsampling algorithms, basically you are cherry picking specific data points instead of getting everything from your data, and then you reduce the volume of data that you are bringing to memory. Imagine you are selecting and scanning a row, and then instead of like piling several rows in your memory, you can just like cherry pick a value that makes sense and have a smaller buffer that you are going to control and let's say feed your buckets with your data. So the other point is that when you have less data, you are going to improve your throughput. So let's say if you don't have a limit, you will always be prone to have ability to get more data than you want, or even let's say if your sensor or something just emits more data than you expect, maybe somehow your system will just slow down and you don't know why. So LLTB is also a good way that you can start limiting your data and your data throughput. So you always know that the limit of data passing through a specific query is stabilized at some point. And you also end up with network optimization. So all your data load will be smaller. And as you transfer less data, you transfer faster, and it's much interesting for serialization and deserialization. So think that everything that you get from your database will end up as a package, and then you need to unpack it, and then maybe you unpack it into your programming language, and maybe you will be downsampling on your programming language. So it's very expensive, and it's much better if you avoid and send only the data that you are really going to plot in your screen or really going to make your analysis. So every time you load data, you are going to pass through a serialization, deserialization process. So what it means like Postgres has like a float type, and then you are in a network, so you transfer it as a string, but at some point it will need to become a float type again, and inside your programming language or like casting it. So depending on how you are using, for example, if you are using like a RM, like object relational mapper, maybe your object and relational mapper will also bring a lot of other utilities, and it also makes it it makes the entire thing much slower because you have more memory load than you need. So be careful with this serialization, deserialization, and you can also observe it on your application when you start using downsampling, that it will have much more limited resources than if you make it open. In the end, your queries will be faster. It will just work in a much faster way than you try raw data. And it resumes in cost savings. So if you define a good way to introduce algorithms for downsampling your data, you will always have savings because you have a better way of querying your data. But you also have a disadvantage. We need to be clear, it's not a perfect thing. And the first thing is precision loss. maybe the type of analysis or math that you are using, you cannot do it because the algorithm may obscure something for you, right? Maybe you have a risk of misinterpretation. So, for example, subsets can be like distorting numbers, or sometimes you need the outliers. You need everything from your data, right? And sometimes it also is very complex how you are going to choose the right downsampling method, maybe to just prejudice your analysis. So be careful. And if you cannot downsample your data, what you can do, you can just like try to think about cheaper storage. As we see a lot of people on downsampling, but like some people, they really have like intensive data and they have like it for 50 years and they really want to have this high resolution data. So probably you need to do like, hey, I need to move it somewhere. Maybe Postgres will not be the best place. Maybe it will be too big, but not because the database will not hold, but maybe because it's also expensive cost to keep everything there. So Parquet files on like S3 like storage would be a much let's say lightweight and cheaper way to provide it. But yeah, you need to do a lot of levels. So at Timescale Cloud, we built something that is called tiered storage that is only for these, let's say, static sets that you are done with them, but you really need to store them in raw, in high resolution, and you really need to query it later, so you can still query as you want. So this is just a line of code as add tiering policy, and then, for example, after a month, your data will be moved to S3, and then it will be very cheap and quite expensive if you want to, expensive in time. So because it's not the same as having the data on your disk, but you also have another network call. But you maybe is able to pay this price of like performance if you are not querying it too much. So that is the Timescale Cloud only feature, but it's a very cool feature. We build it because our users need it, and we already have like tons of terabytes there. And yeah, so this is a very, very progressive project that is doing very well. Now let's go to the project example, because without an example, maybe it's hard to think. So I'm going to introduce this small UI. So this is like just data points from weather data. And here we are looking for New York data. So I'm going to use Ruby because Ruby is my language, and I also built this gem named TimescaleDB. And this is an example of TimescaleDB gem in action. You can just say act as hyper table. And we also have one extra macro that acts as time vector. These both macros allow us to play with several, let's say, query shortcuts that we can just expand the query and just write a nice Ruby code that can make the effort for us. So let's take a look at this. So the first thing that we need is think that we are going to have a scope, and by default, our scope is filtering New York City. And if people select a slice of the graphic, then maybe we will receive this filter param. And the filter param will basically be the edge of the time frame. So we have this edge of the two bounds of what you are selecting, and then we are going to add it to the filter that we want to select. And what we do is like Google Maps. We do an infinite zoom. So we always come back and do the zoom again. And then here you can see the scope. The scope is just this weather metric dot where filter request by param. So you can see this is just like a hash clause. And then we have order by time. So this is a very simple thing. And then we have an endpoint that's LLTB SQL. So you can see here the scope LLTB. And then we have this threshold. By default, we have some threshold there. But we can also choose to put like 5,000 or our screen is like 2000 pixels large generally, so you don't need more than 5000 because you will even not have pixels to demonstrate your entire data on your screen. So we put the limits, and then you can just take a look, have fun, and see it in action. Last step is just the hook of the zoom. When someone just selects a part of the graph, then we got this select, and we do an AJAX call to just refeed it and refetch with the area that we are going to focus. So that's about it. So let's go. And then you can see it from the beginning. So we have here 500,000 rows related to New York City since 80s. So this is 1 hour, 1 hour frame from long time ago. But since 2022, we are watching the API here. So you can see here, this is the part that we are going to concentrate. And then you can see that in the beginning, it was a few points, and then it just gets faster again into the full number of points because we select here 1000 points. So for example, if we wanted to analyze like 2003 to 2004, you can see here, and then you can see also 1000 points for the same 1 year. And then, for example, let's get here, let's say only January, so just a small slice of last December and the beginning of January. And then you see that it was just a small dots because it just uses the dots that was available, the points that were available, and then it refreshes with the 1000 dots again. So you can keep looking the temperature falling down in December, going up a bit, and then falling down in the beginning of January. And that's like 1000 points. So if we don't have the downsampling algorithm, we would just bring everything, and then the UI would do the downsampling because it doesn't make sense to have, or we would just like have these points accumulating here. So for example, if we get even like 3 days of data, maybe now you can see it's still that we have a good resolution. And if we go into, let's say, 2 days of data, we still have like here we reached out the limit of our resolution here. So that's about it, and that's how the downsampling works. And I would like to also show you in the terminal this because I was using another example here, but I'm just going to follow the presentation and come back to it in a few minutes. So so we have 2 algorithms. And the first one that is this one that I was showing you is the LLTB. So LLTB stands for largest 3 triangle bucket, largest triangle of 3 buckets. So as the image shows, it tries to get like what's the largest triangle I can get from a slice of my image. So using the threshold, it tries to maintain the visual characteristics of the algorithm. And I just want to put it this because I was like, how expensive is this and how fast is it? So for example, here you can see like I'm getting like 7,000 records per hour, right? So this is a very little small database. So, but this is just an example to let you understand how cool is this. So for doing this count of the last hour, I spent 24 milliseconds, right? And for just like getting 10 values of this, if I get here only 10 values using LLTB, it's like 28 milliseconds. So it just costs 4 milliseconds to bring some data instead of going and count the data. And it's so fast that and impressive in the sense of like comparing to simple scanning versus this type of technology. So it really can save you memory. It can save you disk reading and several things that maybe for your business that doesn't need a high resolution, it's good enough, right? Another thing that I would like to show you here is ASAP Smooth. So this is the same thing, exactly the same type of query, but it has a different type of result. So the main difference is that ASAP Smooth will follow the trend. So it's more like in the average sense, while the LLTB will try to get the highest peak, the lowest peak, and so on. So that is the most essential difference between the algorithms. They have like similar performance, and we also have the LLTB with gap fill now. So if you have gap fills in your data, you see LLTB will not work very well because you have the gap filling. And now we also have this this function that can track it. It's still experimental, give your feedback, and then we can also promote it to a stable function. So yes. Other strategies. So here are a few strategies. We show downsampling as algorithms. In the past, we show aggregations, and I'm also going to call your attention to histogram. So histogram is just a way that you can store buckets, and from your buckets, you can understand how much data is passing through that bucket. So let's say your data is varying a bit. I am going to show you one example in the terminal here. So for example, here I have an example of the daily of New York, and also we are getting the minimum temperature of the day and the maximum temperature of the day. And then what we do is we go and get the min and max of the day, but we go to the last hour, and sorry, we group data by hour, and then we see where the data is in the sense of the entire day. So let's say in a day your range vary from 0 to 12 or 10 to 35 depending on the day, and then you will build one histogram of 8 values, just like divide the day temperature variation in 8 buckets, and here is the output of the query. So you can see here, for example, 3 and 2. So and then like you have 5, 4, 3, and so you can see here, for example, if you have 4 elements, they will be in 2 and 2 on the histogram. So you can see here from the max and the minimum temperature, the date is just varying and navigating in the middle here. So everything else is zeros. And then you can see these zigzags of the data just coming. So histogram will just make this for you. And we have several other things here. So you can take a look on the other _egg. So we have gauge, we have candlesticks, percentile, stats, and also states, and so on. So take a look on our hyperfunctions. We have the docs, and then you can also think about this type of faster algorithms that you can combine them and use like these aggregations or downsampling when you need to go to the raw data. We can continue. If anyone has any comments, feel free to share on discussion channels. If you are not on our Slack, join our Slack, TimescaleDB.slack.com. And we have a very good community. We also have a lot of other discussions going. We have discussions going on finance and also on metrics now, and AI, LLM, and so on. So feel free to join us, and that is the type of activity that we want to have more folks around. Also, one last call here for office hours. This is like a free one-on-one that you can have with me or with James. And as a DevRel team, we really want to be in touch with developers and folks building things. And if you need any help, any validation of what you're building, or you wanted to talk or have some ideas about benchmarking things, feel free to go to this page. You can just book 1 hour call with me or James anytime. So yeah, I really love these calls. This is one of my favorite parts of my work. I love helping people, and I really look forward to meet you in these calls. Thank you very much for joining. See you next time. Cheers.